Hello, welcome back to Algebra. The title of this lesson is Rules to Multiply and Divide Radicals. So basically in this lesson what we're going to do is we're going to learn some really important properties of radicals that will allow you to simplify expressions that have radicals where you have things multiplied and divided. So for instance, if you have two radicals multiplied together, two radicals divided together, also divided from one another, also radicals when you have exponents, radicals raised to an exponent, various things that you can do to simplify expressions involving radicals. Now in the last section, really importantly, I want you to watch the previous sections of this one if you haven't already, because that lesson I introduced the idea, kind of as a preview, that these radicals, all of these radicals, the square roots, the cube roots, the fourth roots, all of them, really can be thought of, and they really are equivalent to exponents, fractional exponents. And the reason I brought that up is because in this lesson we're going to talk about lots and lots of properties of radicals, such as what happens when you multiply them and so on. And these properties are going to seem like they come from nowhere. They're going to be really odd, just thrown at you, usually in your book with no proof at all. But really, when you realize that these radicals are all just fractional exponents, then you'll understand that every one of these properties in this lesson really just come from the rules of algebraic exponents. In other words, we know what to do when we have two things multiplied together and they have exponents. We know what to do when we have an exponent raised to an exponent. We know how to handle exponents in general. So when you realize that radicals are just exponents that are fractions in the exponent, then it becomes easy to understand where these come from. So just to remind you of that, we covered this in great detail in the last section. But just to remind you, just so we have everybody on the same page, if you have the square root of x, where x is something, right? That is exactly the same thing as x to the 1/2 power. And I said in the last lesson, of course this looks really weird. What does 1/2 power mean? I need you to go back to the previous lesson and watch it because we discussed in great detail what that actually means in terms of a fractional exponent. But even if you don't watch that, if you just know that anytime you see a square root of x, it's the same as x to the 1/2 power. Anytime you see, for instance, the cube root of x, it's exactly the same thing as x to the 1/3 power, right? You see the pattern here. Anytime you have a fourth root of anything, it's the same as the 1/4 power. And just to be complete, because I like even numbers, we'll do a fifth power here. We have fifth power of whatever you have under the radical is the same thing as that thing raised to the 1/5 power. So the pattern is very easy. Square root means a 1/2, you have a 2 in the bottom. Cube root, you have a 3 in the bottom, and so on. So really, when we're doing all of these properties here that I'm going to write down on the board for you, I need you to start looking at these radicals. Yes, of course it means fifth root, third root, or cube root, square root, and so on. But mentally in your mind, anytime you see a radical of any type, I need you to start thinking about, hey, this number really represents an exponent, 1/3 power, 1/5 power, 1/4 power, 1/2 power. Because then when I introduce the properties, it will be very easy to understand where they come from. So let's go over to the next board, the next couple of boards, and write down these properties. I'm going to, in one column, write down the radical property and give you an example of how to use it. In the next column, I'll show you how that property comes directly from the properties of exponents, and we'll do an example like that. So you'll know the radical properties, but more importantly, you'll know how they tie into the exponents and where they come from with a quick example as well. So here I'm going to, in this column, I'm going to call this radical rules. So these are the rules that we're going to be using to simplify these radicals. And over here, I'm going to have call it exponent equivalent. In other words, this is what the rule would look like if you wrote it in terms of exponents. And you're going to see that these radical rules come directly from the concepts of exponents that you already know. So let's take an easy one first. Okay, these kinds of rules will be just thrown at you in a book and you'll be expected to remember them. That's why I want to show you where they come from. If you have, for instance, this is something that will be given to you in a book and you'll just have to remember it, right? If you have the nth root of something called a multiplied by something called b. So n can be square root, cube root, fourth root, whatever n is a number, and I'm taking that root of the product, the multiplication of two things. Then I can write that as the nth root of the radical of a. Notice I've cut off my radical there, so it's just operating on a multiplied by the nth root of that radical operating on b. So this is a good example here in the beginning of properties of radicals that'll be thrown at you in a book. They won't be explaining where they come from. They won't try to prove it to you. They won't say, hey, these are properties of exponents. I'm telling you that so you'll know where they come from. But they'll just tell you anytime you have this, you can write it like this. So what does this really mean? This means that if I have a square root of 2, let's say, a can be anything, right? 2, 3, 5. Square root of 2, where n is a 2 because it's a square root. So square root of 2 times the square root of 3, then I can bring a and b under the same radical as long as I keep the same order of the root. So if it's a square root, it stays to be a 2, for instance. So let me show you exactly where a good example of that. What it's basically saying, it's kind of easier actually to read these from right to left. On a typical example, you might have something like this. Instead of a square root, we'll call it a cube root of 2. And they'll say, here's a cube root of 2 times the cube root of 3. Simplify that. So you see, the cube root is the same in both cases. Notice it has to be the same in both cases. I have a 2 under this one and a 3 under this one. I can combine them, but it still has to fall under a cube root, and it'll be 2 times 3. Which you know is 6. So really what it'll be is the cube root of 6 is equal to the cube root of 2 times the cube root of 3. So that's very useful because if you have a large expression of radicals that are multiplied together, like a square root of 9, square root of 10, square root of x, all multiplied together, you can collect and combine all of those under, as long as the radicals are the same, square roots in my verbal example, you can combine them all, but then when you do that, you have to multiply whatever they were underneath. If it's a third root, then you wrap the whole thing under a third root. If it's a fourth root, you wrap the whole thing under a fourth root, and so on. So again, it's a good example of these properties they throw at you, and I guess you can say I'll just use it, but most students, I mean, I didn't understand, how do you know that's true? I mean, I can kind of use some numbers and show you it's true, but how do you actually know it's true for all numbers? Why is it a property? Where does it come from? So most books don't really teach you that radicals are really fractional exponents until later. Even me, I'm going to do more problems with these fractional exponents a little bit later. But what I want to do is show you that this property of radicals comes directly from the property of exponents. Remember, a square root is something to the 1/2. A cube root is something to the 1/3. A fourth root is something to the 1/4, and so on. So the nth root of anything, for instance, AB here, would be AB to the 1 over nth power, right? Because if it's a square root, it will be 1 over 2. If it's a cube root, it will be 1 over 3. So in this case, it's general, it's the nth root, which means I'm taking to the 1 over n power, whatever root it happens to be, I'll just plug it in there, but it's operating on the product A, B. Now I want you to forget for a second, totally forget that this is a fractional exponent. Just pretend it's just an exponent, because the fact that it's a fractional exponent doesn't change anything. It still follows all of the same rules of exponents that we already learned. So what happens when you have an exponent operating on two things multiplied? We say the exponent goes and operates on the A, and then it also goes and operates on the B, right? It kind of gets distributed into the A and the B, right? So that works for any exponent, no matter if it's a fractional exponent or not. So this would mean that A would have a 1 over n power, and it would be multiplied by B, which would have a 1 over n power as well. It's just kind of, if it were squared, for instance, instead of 1 over n, the 2 would operate on A and the 2 would operate on B. They would be multiplied together. So you see where this is coming from now. What it's basically saying is, now that you know that this represents a root, and this represents a root, it means the nth root of A times the nth root of B, nth root of A times nth root of B equals the product of them, nth root of the whole thing. Product of them, nth root of whole thing. This makes no sense where it comes from because you don't understand what it is until I tell you that these are just exponents, but now you see it as exponents. It makes total sense. If I have them multiplied together with exponents, then I have to, or I can write it as the product of the two and then the exponent operating on the outside, because I know the exponent can then go in. So in terms of a number example, like the one we did here, I can say that 2 times 3 can be written here as 2 times 3. I can operate it as 1/3 power, taking the cube root of it. That would be the same thing as operating this exponent on the 2 and then operating this exponent on the 3. So if you forget these rules, I'm hoping that you'll remember them as I've written them here, but if you forget these rules, then in your mind, start thinking of them in terms of exponents. And then if you see two radicals multiplied together, think of them as exponents. What would I do? I can collect them together and bring the exponent to the outside because I know I can distribute that exponent back in. All right, so that's all of that talking was really just to talk about the very first property here. The next property is the following thing. So here's what happens if I have two things multiplied together under a radical. Next I want to do what happens if I have two things divided under a radical. So I have the nth root of a fraction, a divided by b. So what this means, and you'll see in a book, is you'll have the nth root of a can be brought as its own radical, and the nth root of b can be brought as its own radical. So what it's basically telling you, it's often easier to read them from the right to the left. If you see a fraction with a radical divided by a radical, I can collect them under the same radical, but I have to, of course, keep a divided by b, and I have to have the same order of the root. So it has to be a square root and a square root, for instance. Then the radical that wraps the whole thing would also be a square root. Okay, so these are kind of like cousins of each other. If I have two things multiplied under a radical, I can break them apart. If I have two things divided under a radical, I can break them apart. Or going the other way, if I have two radicals multiplied together, I can combine them. If I have two radicals divided, I can combine them and bring them under the same radical. Again, the order has to be the same. So an example of that would be, let's change colors a little bit. An example would be, for instance, if the fraction under my radical were 2/3. And I was going to operate on that with just a square root. So I'm not going to put a 2 here because we know it's a square root. Oftentimes you'll see this, you'll see a fraction, and the question is simplify the thing. Well, the first thing I can do is I can break this up as square root of 2 over square root of 3. Or going backwards, if I were given this expression with a radical on the top and bottom, I can combine them and bring them under a common square root. Now again, looking at this, you might believe me that it's true, but there's no intuitive reason for you to believe it. I mean, I'm telling you it's true, but you don't really actually know why it's true. But then you should start thinking, these things are really exponents. So let's try to rewrite this in terms of its exponent form. What we're saying is fraction a over b, but instead of wrapping a radical around it, we'll wrap it to an exponent of 1 over n. Now what happens when you have a fraction raised to any exponent? Forget the fact that it's a fraction. The exponent applies to the numerator, and then also the exponent applies to the denominator. We learned that a long time ago. So that would be a to the 1 over n divided by b to the 1 over n. You can think of it as almost like distributing in, kind of, and operating on the top and operating on the bottom. So you see what you've written here is you've said that the square root of a, or the nth root of a, I should say, divided by the nth root of b is equal to collecting them under the same radical, which is the square root, or the nth root. So as long as n matches, it works for any of these radicals, no matter what we have. So if we wanted to write this exact problem under here, and 2/3 operated as a square root around it, let me write 2/3 and write it as the 1/2 power, right? Instead of just this radical sign. Then I can operate the 1/2 on the top as an exponent, and I can operate the 1/2 on the bottom as an exponent. You see, the radical is the same in all cases, so now you see where it comes from, because this is an exponent that can be distributed or kind of like taken in to operate on the numerator and denominator. So it goes both ways. If I have radical on the numerator and denominator, like a square root, I can bring it under a common square root, or I can break it apart depending on what I'm trying to do in my problem. All right, that's the second important property. How many more do I have? I'm not sure I'm going to be able to fit them all on this board. Maybe. I think what I'm going to do actually is I'm going to go to this board. We're going to do the same thing here. I'm going to have the radical version here, and then I'm going to have the exponent version here. Okay, now these next two are, these over here are very easy to understand once I've kind of boiled it down for you. The next two are not at all obvious. When you first look at them, you think, well, how can that be? But then when we write it in exponent form, it's very obvious where it comes from. That's why we're going to do it. So the next property is the following. If I have something, call it b, right? Raised to an exponent, we'll call it m. I have no idea what these are. B and m, can be anything. And then I take and wrap a radical around that, and it's an nth root, right? So I'm raising b to an m power, but then I'm taking an nth root, and m and n are not the same. That's why I use different letters. So for instance, this could be 2 to the 3rd power, but taking the 4th root. Or this could be 3 to the 5th power, taking the square root. So they're all different, basically. What this means here is that actually the property that I'm teaching you here is that I can take this exponent and actually bring it outside of the radical completely. For instance, I can also write this as the nth root of b and wrap parentheses around it and raise it to the nth power. Now, I don't know about you, but this actually, to me, just looking at it without knowing anything about exponents, it's kind of like, how do you know that's true? That's my first thought. You have an exponent inside of here. Like I said, b to the 3rd, like it could be 5 to the 3rd power, but then taking the square root. But what I'm telling you is, I can take this exponent completely outside and do it last. In other words, here I'm raising b to some power and then taking the nth root. And here I'm taking the nth root first and then raising the result to the nth power. So what you've basically done is you are interchanging the order. And what I mean by the order is, here I did the exponent first, then the root. Here I did the root first, and then I did the exponent. And what this property is telling you is it doesn't matter which direction you do those or which order you do those. It's kind of like multiplication, right? 2 times 3 is 6, and 3 times 2 is also 6. Or if you even have more numbers, like 2 times 3 times 4 is the same as 4 times 3 times 2. It doesn't matter what order it's in. We all know that about multiplication. But it's not obvious when it comes to roots and exponents until you start thinking about it for a minute, because exponents really is multiplication, and roots really is kind of like multiplication also, but it's collecting common factors together. So it's kind of like a reverse. It's almost like division, really, which is an inverse of multiplication. So it kind of makes sense that you can do them in different orders, but that's still not strong enough for a solid proof for me. So what I want to do is show you an example and write it as an exponent, and then we will get the idea here. So let's look at this guy as an example instead of talking about it. So inside here, b to the m, let's say we have 2 to the 4th power. But then after I take that 4th power, I'm going to take the cube root of the result. I do the inside first, then I take the cube root. What this property is telling you is that I can actually instead take the cube root first and then take the result of that and raise it to that inside power. It's like you just grab it with your fingers and pull it out. It doesn't matter the order you do it. Exponent, then cube root, then exponent. Again, not so obvious, really, in my opinion. But let's go ahead and write it as an exponent, and I think it's going to be a lot more obvious. All right, now what we're going to do is rewrite it as an exponent and see if we can understand a little more cleanly where it actually comes from. So this is b to the nth power. So if I was going to write that, I would call it b to the nth power, just like any exponent. But then the result of that has a nth root applied to it. So as an exponent, you would wrap that in parentheses and call it 1 over n. That's an nth root of whatever's on the inside, right? Square root, cube root, whatever it is. But now we know that we can clearly see this is an exponent raised to an exponent. Anytime you have an exponent raised to an exponent, you just multiply the exponents. It doesn't matter one of these exponents is a fraction, you still end up just having to multiply them. So what is m times 1 over n? That's just going to be b to the m over n. This m times 1 over n gives you this. But then you look at this again and you say, well, it's a fraction. So I actually could write it like this. Instead of m over n, I could write it as 1 over n first, and then I could take the result of that and I can raise that to the nth power. Why can I do that? Why can I interchange the order? Because when I have exponents raised to an exponent, all I do is multiply them. So m times 1 over n gives me this, but 1 over n times m also gives me this. That's why you can interchange them, and that's why it's so much better to think about these cubed roots and all that as exponents. Because all of these weird properties like, oh, I can just take the interior exponent, I can pull it out of the radical, they don't make sense as radicals, but when you think of them as exponents, it makes perfect sense why I can interchange them, because whether I have m raised to this power or this power raised to this power, it gives me the exact same thing, no matter the order I do it, because multiplication doesn't matter the order I do it. So in terms of a number, or in terms of an example like this, it would be like this: 2 to the 4th power, right? 2 to the 4th power raised to the 1/3 power. So I'm taking the cube root of what's inside here. What I'm basically saying is that I can multiply these together. So this is going to be 2 to the 4/3 power here, if I multiply 4 times 1/3, but I can also write that as 2 to the 1/3 power, doing that part first, doing the cube root part of it first, and then raising it to the 4th power. If you get a calculator out and you take 2 and raise it to the 4th power, and then you take the cube root, and then figure out what that answer is. And then separate calculation, you take the cube root of 2, and then raise the answer to the 4th power, you're going to get the same exact answer. So that's a kind of a good way. Also, I mentioned this before in the previous lesson, but when you see a fractional exponent that looks like this, where it's 4/3, the way you read it is, I have to take a cube root, and I have to raise the thing to the 4th power, but the order actually doesn't matter. I can either raise it to the 4th power and then take the cube root, or I can take the cube root and then I can raise it to the 4th power, and these are the reasons why it doesn't matter. It's because I'm able to write those exponents in any order because all I'm doing is multiplying the exponents anyway. That's why this property, even though it looks like you're just magically doing this, it's like, how can that be? That's why it works, because these are just exponents. So the order really doesn't matter. All right, we only have one more property of addition and, of multiplication and division anyway. And this one's a little weird, but again, very easy to understand with exponents. If I had, for instance, something, we'll call it b, and I'm going to have a radical, but instead of just a single thing out here, a single number out here, I'm going to call it n times q, right? It's still a 4th root or a 5th root or whatever, but I'm going to write it as a product. You'll see why in a second. Then I can write that as follows. I can write that as the qth root, for lack of a better word. I can write that as the qth root, right? Let me go ahead and write my q a little bit better. Something like this. And then I can, on the outside of that, I can have an nth root wrapping it. What it's basically saying, it's a little bit easier to read it going this way. What it's saying is if you have nested radicals, where you have a radical and then you have an outer radical, almost like nested parentheses, right? You know from order of operations you have to do the inside radical first and then the outside radical. So if I were going to do this, I would do the qth root of b. Whatever I get as the answer, I would then take the nth root of it. But equivalently, I can actually write it as a single radical, where what I actually, the order of the radical is the product of n times q. Again, it's another one of those properties that doesn't make sense unless you think of them as exponents. So we'll do that in a second. Let's, before I go and do that, let me go ahead and write down what it actually would look like, because it'll be easy for you to understand. For instance, let's say I'm going to take the 6th root of the number 3. 6th root. But I know that 6 can be written as a bunch of different things. It can be written as 2 times 3. So I know that I can write this as, this 2 times 3 means that I'm just taking 6 and I'm writing it as the product of 2 times 3. Notice I have just like n times q here. So what it's basically saying is that I can then write this, if I want to, as, I'm going to go ahead and write the square root with a 2 there, even though I don't really have to. I can write it as the square root of 3, and then the answer to that has a cube root applied on the outside, or equivalently, I didn't really show it up here, the order really doesn't matter. I can actually take the cube root of 3 and then take the square root on the outside. So it's kind of like before where the order doesn't matter, but this one really applies to nested square roots. So this is called nested radicals. And the reason I say that is because usually you're not doing this and going the other way. Usually I'll give you a problem where I'm giving you, you have the square root of 3 and then the cube root of the result. And I'm telling you simplify that. So then what you're going to want to do is make it the 6th root of 3, because you have 2 roots with different bases. You can multiply those bases and create a new radical with the multiplication of those bases, and it doesn't matter the order in which you do them. Okay, so you might believe me. You might say, okay, that's great, but why does it actually work? Well, let's go all over and talk about it in terms of exponents. Let me go ahead and draw a little dividing line for this one so I can make sure and not clutter things up. This would be written as follows. You would have b raised to the power of, but the power is actually the product here, so it would be raised to the 1 over n q. It's still a radical where the order of the radical is just n times q, right? Whatever it is, like 6, for instance, it would be 6. But I can write this as follows. I can write this as b raised to the 1 over q, but I can take, let me do it with brackets. I can take the answer to this and I can raise that to 1 over n. Make sure you understand it. right? What's going on here is I have a power raised to a power. If I have the qth root of b, and the answer to that is I take the nth root of that, how would I simplify it? It's an exponent raised to an exponent. Again, it's just rules of exponents. Anytime you have an exponent raised to an exponent, you just multiply them. 1 over n times 1 over q is going to be 1 over nq. So what it's basically telling you is if you have nested square roots and you can do this, this doesn't look so obvious. But here it's an exponent raised to an exponent, and it makes total sense that the answer will be b to the product of those because you're having an exponent raised to an exponent. So a qth root and then taking an nth root of the result is the same as taking a single root where the order of the root is the product of them. The reason is because of the exponents. And I'm not going to write it here, but you can also interchange the order of these. It could be 1 over n here and 1 over q here, because when I multiply them, I'm going to still get the same thing. That's what I was telling you here. The order doesn't matter. So if I were going to write it down in terms of numbers, like this example, 3 to the 6th power, it would be, or the 6th root, it would be 3 to the 1/6, that's the nth root. But I know that 6 can be written as 2 times 3, right? So I can write this as 3 to the 1, let me see which way I did it here. I can write it as 3 to the 1/2. Well, you know what? I'm going to write it like this. 1/6 can be written as 1 over 2. Let's do it like this. Times 1 over 3. I know that 2 times 3 is 6, 1 times 1 is 1, so 1/6 can be written as 1/2 times 1/3. But that can be written as 3 to the 1/2 raised to the power of 1/3, because I can multiply these two exponents, exponent raised to an exponent, I multiply them, that's what I get back, but also the order doesn't matter. I can write it if I want to like this, 1/3, and then 1/2 power. Like this. So in terms of numbers, that's what it would look like. In a problem, if I have a cube root and then I have a square root of the answer, then of course I can multiply them and make it a 6th root. That's what it looks like in terms of exponents. This is what it looks like in terms of radicals. I've tried to present the properties to you, showing you the properties of the radicals, but then also showing you the properties if you write them in terms of exponents. Because when you think of them in terms of exponents, they actually make a lot more sense. So what we're going to do in the next few lessons, we're going to use these properties of radicals. I'm going to give you large expressions, and we're going to say simplify this radical, right? And later on, and there's going to involve multiplication and division of radicals. That's what most of these properties are dealing with. And the goal of when we simplify radical expressions is really two main things. Of course, we want to take all of the roots that we can, but there's two main things that you want to watch out for. I'm not even going to write them down because we're going to use so many problems it's going to be obvious. Two things to simplify a radical. At the end of the day, we do not want any fractions under a radical. We don't want any fractions under a radical. So notice we had some properties where we said, here's what happens when you have a fraction under a radical. We break it up, and then we simplify it further. We don't want any fractions under a radical. It's not that it's wrong, it's just typically when we call it simplified, we don't want fractions under there, so we're going to break them apart. Second thing is we, in the final answer, don't want any radicals in the denominator of a fraction. So like 1 over square root of 2, we want to get rid of the square root of 2 somehow. That's called rationalizing the denominator. I'll teach you how to get rid of those as we get into the problems in the next lesson. But basically, two things. We don't want any fractions under a radical. We don't want any radicals in the denominator of fractions. It's not that those are wrong, it's just convention that when we say something is simplified with a radical, it doesn't have either of those things, right? So we don't want, when we're simplifying, we don't want 1/3 under a radical. That's not simplified. And we also don't want 2 over the square root of 3. That's not simplified. We're going to learn how to break these apart and get rid of that fraction under there. We're going to learn about how to get rid of these radicals that are in the denominator. And we're going to use all of these properties along the way to simplify radical expressions. So follow me on to the next lesson, and we'll get started right now.